Hello my dear students. So today let us start with exercise 1.1. As today I have just explained the introductory part of the chapter. Let us go with the exercise now. Exercise 1.1, question number 1. Determine whether each of the following relations are reflexive, symmetric and transitive. In which category does it really falls? Let us understand the questions. The first question is given: relations are in the set A, where the set A has the following elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 13, 14. Defined as relation is equal to x comma y, and the relation is defined like that: 3x minus y equal to 0. So whatever value you put, it should satisfy this relation, this defined relation. So now let us proceed with it and see whether in which category does it really falls under. So x comma y. So how can you really see this in here? What is given here? 3x minus y equal to 0. That means 3x equal to y. Certain. Alright. Now let us see the relations here, and the limitation of the elements are 1 to 14 only. We cannot exceed the value more than 14. So let us find the element present in these relations. Number 1. If we take x1, what possible value you will get for y? 3 1 ja 3, means 1 comma 3 is the first element of the relation. Now let us consider x2. If you consider x2, then how much you will get if you consider x2 here? 3 to the 6, then y will be 6, 2 and comma 6. If you consider x3, 3 3 is 9, y equal to 9, If you consider x4, what is the possible value of y? The possible value of y is 4 3 is 12, that means 12. Now if you consider now x, the value of x is 5, what will be the possible value of y? 5 is 15. But you can see that 15, the number 15 is not in the set. It is exceeding the limit of set. So this element is not present in this relation. Therefore the elements of these relations are 1, 3, 2, 6, 3, 9 and 4, 12. So this is the perfect defined relation based on this these definitions of the relations is provided in the questions. Now let us see whether it is a reflexive. Do you remember what does reflexive really means? Reflexive means what? Reflect. वापस अपना नंबर वापस होना पड़ेगा. Means 1, 1 means a, b, b. These are should present in the relation. So can you see here the repeated number 1, 1 is there. Though 1 is here in the set, but 1, 1 is missing. 2, 2 is missing. 3, 3 is missing. Do you remember that statements? What does the reflexive relation says? A should be belong for all a belong to a. So here 1, 1, 2, 2, 3, 3 does not belong to the relation. So it is not a reflexive. I hope you got it. What do I really meant to mean? So what you come to know that this is not a reflexive relation. Alright. Now let us proceed with the next type of symmetry. Let us check whether it is symmetric relations or not. So what we come to know means what we have seen yesterday, that what is reflexive? When the reverse order is also present. If 1 2 is there in the relation, then 1 must be there in the relation. Then only we can consider it as a reflexive relation. Can we see 1 3? Yeah. Is there any 3 1 can be seen in this relation? Not at all. So we can say that this relation is not a symmetric as well. Clear? Also we can write that it is not a symmetric relation. So for concern of definition. So also A1 A2 belong to R, but A2 A1 is not belong to R. So the definition is not fulfilled. So we can clearly state that without any remark, we can clearly state that it is not a symmetric relation. Therefore it is not a symmetric relation. I hope it is crystal clear, everyone. Crystal clear. Got it? Now let us move to the next part, that is your transitive. Whether it is really transitive. Let us see. Is it transitive or not? So do you remember the formula for definition or not? What does transitive says? Transitive says that if A1, A2 belong to the relation, also A2, A3 is also belong to relation, then there must have to be this one. A1 and A3 should also be present in the relation. Then only we can clearly state that this relation is a purely transitive. So far concerned, let us proceed with these statements, as the space is not there, limited space. So let me clear it up and say whether it is a transitive statement. So you can see here is 1, 3 is present, means A1, A2. Okay. Also A2, A3 means A2, A3. But can you see A1, A3? Not at all. Chaiya, chaiya, chaiya. Oh, Mary. Chaiya, chaiya, chaiya. You can see here 1, 3 is present and 3, 9 is present. But you cannot see 1, 9. As first concerned, you can see A1, A2 belong to relation. A2, A3 is also belong to relation. But 1, 1 and A2 are not belong to relation. So we can clearly say that it is not a transitive relation. Let us write where? Where shall I write? Come on, let me write here. So after that statement, after these statements, the second statement, third statement I am writing here for more better reference. As the space concerned here, let me write it transitive. So transitive case, transitive. Why? Here you can write 1, 3 belong to R. Also 3, 9 belong to R. But 1, 9 is not belong to R. Is not belong. ऐसे लिखो, not belong to R. Therefore, it is not a transitive relation. It is not a transitive relation. Transitive relation. I hope it is clear, everyone. Whoever looking in this video, I hope it is clear. The quarantine is quite long, man. I can understand the feeling that you are really processing on. Okay, come on. As what? It is not a transitive. Because for being transitive, let me repeat one again. If A1, A2 present in the relation and also A2, A3 belong to relation, so there must be the presence of A1 and A3. Then only we can clearly say that it is a perfect transitive relation. So ultimately what we come to see that it is neither transitive nor reflexive nor symmetry. Nothing. It is nothing. We are nothing. Thank you. So here is our next part of this question, that now next question says that relation R in the set N of natural numbers defined as R is equal to x comma y and y equal to x plus 4 and y is less than 4. X is less than 4. X is less than 4 and x is what? X is a natural number, and we know that natural numbers start from 1, 2, 3, 4, 5, infinity. So here let me put the respective value of a1 and of the x and y and see the ordered pair. What are the possible numbers of elements present in the relations? Here the relation are what? If you put x1, what will get? y6, 1 comma 6. If you put x2, what you will get the value of y? Y equal to x plus 5. X is already 2, then x plus 2 plus 5 is what? 7. If x is 3 plus 5 is what? 8. If x is 4, then 4 plus 5 is what? 4 plus 5 is what? 9. I hope it is clear. Therefore, the elements of the relations are as follows: 1, 6, 2, 7, 3, 8 and 4, 9. Clear that? So let us see through our Chetan mind whether it is a perfect respective relation or not, whether it is a reflexive, symmetric or transitive. Whether see, is there any repeated or the same ordered pair is present? 1, 1, 2, 2, 3, 3, 4, 4 are present? No, not present. Here A comma A does not belong to R, so it is not reflexive. It is not reflexive. Can you see? Is it a symmetric relations? No, it is not a symmetric relation because the reverse order is not present. The reverse order is not present. 1 6 is present, but 6 1 is not present. 2 7 is present, but 7 2 is not present. 3 8 is present, and 8 3 is not present. I hope it is clear what I am saying. So also 1 comma 6 belong to R, but 6 comma 1 is not belong to R. So it is not transitive. Sorry, so it is not reflexive. So it is not symmetric. Now let us proceed to the next font of relation transitive. 1 6 is present, but 6 nothing. 2 7 is present, but 7 nothing. 3 8, no, it is absolutely not transitive also. Here you can write A1 comma A2 is belong to R, but means A1 A2 belongs, but 6 something is not present, but A2 A3 is not belong to R, so it is not transitive also. It is not transitive also. I hope it is clear. So we come to know that it is neither reflexive nor symmetric nor transitive. Clear? Next, let us proceed to the next question. So here goes our next question. It says that relation R in the set A equal to 1 2 3 4 5 6 as R is equal to x comma y is divisible by x. It is said that the y is divisible by x. Now let us see the possible ordered pair or the possible element present in these relations. So R is equal to what? R is equal to, what are the possible? If I take 1 1, yeah, you can see y is divisible by x. 1 is divisible by 1. Can I use 2 2? Yeah, obviously 2 2 is also under this relation because the value of y is very nicely divisible by x. Is this is possible? 3 comma 3? Obviously 3 comma 3 is also fall under this relation. 4 comma 4 also obviously. 5 comma 5, 5 comma 5, 6 comma 6, these all are possible ranges of the relation. And any more thing? Yeah, if I take 2 1 2, is it in this relation? Obviously you can see, just see the definition what it is said. X comma y is divisible by x, y is divisible by x. If y is 2, y is divisible by x, means you can divide 2 by 1. Similarly we can proceed with 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6, 1 comma 6 is extreme limit. Any further? Yeah, we can see 2 comma 4, yeah, obviously y is divisible by x. 2 comma 6 and also 3 comma 6. These are the following element present under the category of this relation. Now let us proceed with the following concept, whether it is reflexive, symmetry or transitive or not. But from this relation, can we see 1 and 2 to 3 4? Yeah, all the repeated identity elements are present. So we can say that this relation is valid reflexive relations. Here what we can write? Here A comma A belong to R for all A belong to R, या फिर A belong to A. So it is what? It is your reflexive. It is a reflexive relation. Now let us proceed with the next statement, the next relation, that is symmetric. Whether this is symmetric or not. Can we see 1 2? Is 2 1 is present? I don't think so. It is not present here. Here 1 3 is present. Do 3 1 is present? 3 1 is present? No. how can you say it is a symmetric? It is not a symmetric, as the following important things are missing, so we can consider it as a symmetric. But we can say that next statement here 1 comma 2 is present, 1 comma 2 belong to R, but 2 comma 1 is not belong to R, so it is not what? It is not symmetric. Symmetric relation. The last is transitive. It is. Now let us see whether it's transitive or not. 1 comma 1, 1 comma 1, 1 comma 2, 1 2 is not present. You can see 1 A comma A2, A2 A3 is present, but 1 comma 2 is not present. It is not transitive. 1 3 is present, and 3 3 is present, but 1 3 is not. 1 3 is also present. Yeah. 2 comma 2 present, and 2 comma 6 present. 2 comma 6 is all present. So something is missing. That is, you can see that here. So now let us come to the last statement for the transitive here. So what can you say? This is very interesting factor. It's very interesting factor. It's very interesting. Let me clear it up. If A comma B belong to R, obviously, because that means what? The B is divisible by A. I consider A, B are the elements of the relation, okay? And if A, B are belong to the relation, that means A, B divisible by A, means A can divide B, and B, C also belong to R. It's a very clear concept. That means what? C is divisible by B. C is divisible by B. Then I can easily consider that A comma C is also present in the relation. Then A comma C will also present in the relation. Manlo, anything, whatever we consider. If suppose 1 comma 2 present in the relation, and 2 comma 4 is also present in the relation, can I say 1 comma 4 is also present in the relation? Obviously 1 comma 4 will definitely present in the relation, because if 1 divides 2 and 2 divides 4, then obviously 1 will divide 4 also, na? I hope it is clear. Can you catch what I am saying actually here? This is the important thing that I like to mention here. So therefore we can say that therefore we can say it is a transitive relation. It's a transitive relation. I hope it is clear, my dear. Now let us proceed to the next question. So here is our next question, question number 4. Means 1 to 4. Relation R in the set Z for all integer defined as R equal to x comma y, where x minus y is an integer. X minus y is an integer. It's a very simple factor. Now important thing comes here that x comma y is an integer. What does integer actually means? Integer actually means all the positive and the negative numbers including 0. So if it is a number line, every numbers 0, 1, 2, 3 to go extend in the directions, infinite positive side, you will getting all the integers. If you go negative side here, minus 1, minus 2, minus 3, and it goes on. You can go back side forward. It's equal. So where x minus y is an integer. Obviously let us proceed. So actually it seems like it is an infinite relation. Why so? Because x minus y is an integer. Whatever value, you can take the enormous number of value here. That means if you take x as 1, what you will get, you can take y as 2 also. You will take any random numbers, because if you divide any random numbers, you will definitely gonna get a integer numbers. That means any number. If you subtract 1, 1, is it fit in this definition? obviously it fit in this definition. Why so? Because x comma y is x minus y should be an integer. If I subtract 1 minus 1, what you're going to get? You're going to get 0, and that is an absolute or a perfect integer. If you mention 2 comma 2, it is also a relation. Why? Because it falls under this category of definition. You consider 3 comma 3, yeah, it is also a integer. Means 3 minus 3, you're gonna get a integer number. So on. Any numbers you will put. Suppose if I put now 1 comma 2, it fit in definition obviously, because x minus 1 should be integer. So 1 minus 2, what is that? Minus 1, which is an integer, definitely. If I put reverse it, 2 comma 1, is it fit in this definition? X minus 1 is integer, means 2 minus 1 is what? 1, which is also an integer. So what we come to see that it seems like it is following all the rules. It is following a reflective rules also, symmetric as well as transitive. Let us see for the transitivity. So now for the transitive case, if I say 1 comma 2 presents in this relation and 2 comma 1 is also present in relation, then 1 comma 1 is also present in this relation. That means a1 a2 present in the relation, a2 a3 present in the relation. That means a1 and a3 is also present in the relation. It is perfect transitive. So we have to write a statement. Why you can say, how you can say that these are reflective, symmetric and transitive. Though we cannot write all the elements of the relation here, because it is the relation of infinite sequence or infinite series. Clear? Infinite numbers of elements are present in this relation. So we cannot plot the numbers of all the relations, order of pair all the relation. It is not possible. So there is a different methods, a different way to express the relation here. Let me make you understand how to express the relation here. It's a more nice, better way. See here, to express the relation and to write whether it is a reflexive, symmetric or transitive. How can I do that? For reflexive, let us write for reflexive, reflexive. For reflexives, what we are going to do is that we can write that as a minus a equal to 0. Definitely we have already seen. If you take same number 1 comma 1, you are going to get 0, which is an integer, and a comma a is an integer. Definitely 0 is integer. So we can take any same number 1 1 2 2 3 3. You are going to get 0. So and it is symbol for all a belong to z, means whatever number you take in this a are the element present in the set z, z. So that means therefore what we can write, a comma a belong to the relation for all a belong to the integer. Therefore it is a reflexive relation. Therefore it is reflexive. Clear? I hope it is clear. Let us proceed to the next statement or next point. It is symmetric. Let us check whether it is symmetric or not. Symmetric. So as we can see here, as a minus b is belong to the relation, is as a minus b and b minus a are the integer. Are integer. For all a comma b belong to z. For all a comma b belong to z. That means what we can write, that a comma b belong to R, also b comma a is also belong to R. So definitely we can say that R is symmetry. Therefore R is symmetry. Now let us proceed to the next statement, that is transitive. Whether it is transitive or not. Transitive. For transitivity, let us see transitivity. The case of transitivity. Let us write here. Transitivity. S, we can write as a minus b and b minus c are integer. You can see here as a minus b and b minus c are integer, as a minus b and b minus c are integer, and a minus c is also integer, and a minus c is also integer. That means what? A minus b means what? A minus b means x minus y, what I have mentioned here. A minus b and b minus c are integer, and also a minus c is also integer. Therefore, here what we can write, I can see, see. So here, what we can write, a comma b belong to R, b comma c belong to R, also a comma c belong to R. Therefore, it is transit. Therefore, it is transitive. Therefore, it is transitive. So, we found that ultimately this relation is all follows the case of transitive also, reflexive as well as symmetric. Let us proceed to the next part. So, here is the last part, means the last part of the first question. It says that relation R in the set A of human being in a town. Set A is a human being in a town. Suppose consider this is a town of set A. A lot of human beings are there. Suppose P, Q, R, S, T, U, V. These are all human beings. Now the human beings are present in the town at the particular time. Okay, fine, great. So the relation R is given as like that: x comma y, where x and y work at the same place. Where x and y work in the same place. If consider x and y work in the same place, can I say x comma s is also working in the same place? Obviously. And y comma y is also working in the same place. X comma y comma x are also working in the same place. Are you getting our issue? Okay, means example, so Pooja and Ranjit are in the same town. So can I say Ranjit and Pooja are also in the same town? Obviously, it's not a big deal, not a difficult case here. So it is also a symmetric also. Let us see the case for transitivity. If consider x comma y, means A, B present in the town and B, C also present in the same town, can I say that A comma C is also present in the same town? Definitely. So it means it's kind of satisfy all the cases of reflexive, symmetry and transitive. So here what I can say here, A comma A also belong to R, I can say, and also A comma B belong to R, and B comma C also belong to R, even though A comma C also belong to R. A comma C also belong to R. So therefore we can say, so it is reflexive, symmetric and transitive. These following the three rules. Now let us see the next question, that is what your B part. R equal to x comma y, where x comma y live in the same city. If x comma y means, let us consider A comma B. Can I say A comma A are in the same town? Obviously, it also belong to R. Can I say if A comma B belong to the same town? Can I say that B comma A is also belong to the same town? That means it is also the case of a symmetric. Now let us see the third part, that is if A comma B belong to the same town and B comma C belong to the same town, can I say that A comma C also belong to the same town? Obviously, A comma C also belong to the same town. Not a big deal. Clear? Exactly. Now let us see the next part here. Question number C. R equal to x comma y. R equal to x comma y, where x is exactly 7 centimeters taller than y. Where x is 7 centimeters taller than y. Let us see what we can say regarding this. Alright. x is 7 centimeter taller than this. Consider, can I say that a comma a belong to R? No, obviously not. Why? Because a, if you subtract a minus a, will you get 7? 7 means will you get 7 times taller? मतलब कि if I subtract my height with my height, can I get 7 less than my height? Are you getting what I am saying? No, absolutely not. So it is not a reflexive. It is not reflexive. It is not reflexive. It is not reflexive. If I say a comma b belong to R, then can I say b comma a belong to R? No, definitely no. If the subtraction of the height of a and b is 7, if I reverse it, b comma a, will you get 7? No, you won't get 7, you get minus 7 for that. Third is also not possible, because why? If a comma b is belong to R and b comma c also belong to R, if a is 7 means 7 times or 7 centimeter less than b is 7 centimeter less than c, then what? A and c is 7 centimeter less than c, or what? No, definitely not. So it is not a transitive also. So what we can write? It is not a transitive, reflexive and symmetric too. It is neither of the three. Third part, x comma y. X is the wife of y. X is the wife of y. Can I say here a comma a belong to R? Not. Do x is the wife of x? Can somebody become a wife of himself or herself? What is this? So no, definitely not. It is not possible. Now it is not reflexive. We can't do not reflexive. If I say a comma if a comma b belong to a relation, that means x is the wife of b, can I say b is the wife of a? It is not possible. It is not possible. Assured. Now one more case, last case. If a comma b belong to the relation, that means what? A is the wife of b, and b, how can we be the wife of another? How can we be? B can be the wife of another. A is the wife of B. And it says that B is the wife of, means A is the wife of B. How can a person can be acting as both wife and husband in a individual case? Not possible, man. So crazy question. It's a really very crazy question. So it is same thing. It is neither not a reflexive, not a symmetric, or not a transitive. So you can follow the same thing here. You can write the same thing. Last question. X is the father of y. Can I say here a comma a belong to R? Not y. Why can't we say कि खुद अपना बाप हो पाएगा? Do a father can be his father, own father? Not at all. Same thing like the previous question. Can I say a comma b belong to R? Yeah, I can write that a is the father of b. And can I write b is the father of a again? It is not possible. It is not asymmetric. Now let us see the last part of this. Means if I say next part, if a is the father of b, okay, come on, belong to R, and b is the father of c. If a is the father of b, then how can be a is the father of c? Give to the grandfather also. So but also belong to R, but a comma c is not belong to the R. So it is also same case, not transitive, not reflexive, no symmetry. I hope it is clear, very clear. Keep it up, man.